Okay, so we have studied front-end design, which includes branch prediction and the instruction fetch for wide issue superscalar. Okay, so maybe we can supply good instruction stream using the front end we have studied. Let's move this to the back end and the pipeline. The first issue is out-of-order execution. Out-of-order execution, which involve data dependence. So, programs usually have exhibit three different types of data dependence. The most fundamental dependence is called true data dependence, and it's also called read after write. You have to read some data after the producer writes. Okay, this actually corresponds to producer-consumer relationship. You cannot read data until the producer produced. Okay, this is called read after write dependence, or true data dependence, or it's also called flow data dependence. So if you implement sequential non-pipelined machine, then all these dependencies should be satisfied because it's sequentially one at a time. Every previous instruction have completed, so you don't have to worry about this data dependence. It's automatically satisfied. But in a pipelined architecture, because you overlap the execution of instructions in the pipeline, sometimes this data dependence can be violated. Then you have to prevent that violation. You should preserve all these data dependence to produce correct program output. Okay? So, we are trying to read some data. So let's go back to the beginning, the pipeline. Assume you have simple 5-stage pipeline. Fetch, decode, and read source operand, and do the execution, computation, and write back. Fetch, decode, read, execute, write back. Okay? So you are trying to read, so let's look at the instruction at the read stage. You are trying to read some registers. Okay? But the producers are still in the execution or write back stage, which means they have not produced into the register file. So if you are trying to read from the register file, it will cause problem because you are reading old value, because the producer is still in the pipeline. Okay? So you need pipeline interlock, which means it should wait until the producer complete and write to the register file. Okay? To do that, you need to compare the source register number with the producers, with the instructions in the pipeline, already in the pipeline, or the destination register number. If the destination register number matches the source register number in the read state, then there is a read after write dependence. And this dependent instruction at the read stage must be stored until the producer completes. Okay? And this is called pipeline interlock. You need to check the dependence, and whenever there is a dependence, you have to store the pipeline, which means you have to stop this instruction. Then the following instruction at the decode stage and fetch stage need to be stopped as well, because they cannot go forward because it's blocked by read stage instruction. Okay? This is called pipeline interlock. Sometimes, but this kind of data dependence, read after write dependence, occurs quite often. Okay? You write into register R1 and you are reading from register R1. And every time you have this dependence, then pipeline has to be stopped frequently. This will slow down your pipeline. Okay? To accelerate or to remove this dependence, one way is you don't have to wait, because at the read stage, you have execution stage. At the read stage, you are trying to read instruction from the register file, but it's not ready because the producer is at the execution stage or write-back stage. Okay, but if you look at the end of this read stage, or at the end of execution, same cycle, they have produced. They have done the computation from the ALU. The result is available, but they have not written to the register file. Right? So in that case, we can use bypass, which means instead of waiting until producer writes to the register file, you can send this data right away to the waiting instruction. Okay, that's called bypass. So for the read stage instruction, there are two options. One is you can either read from the register file, which takes some time, or you just grab the data from the ALU and bypass. Okay? If the ALU computation time plus this wire transmission delay is equal to register file access time, then you can choose either one. Okay? I can either read from the register file or I can bypass from the ALU. If I can bypass from the ALU, then I don't have to store. Okay? You bypass and move on. Okay? For single cycle, if the computation takes short amount of time, single cycle, then you can bypass easily. Okay? But if your producer, this computation takes 2 cycles, then you have to wait at least 1 cycle because the data will be available at the next cycle at the end. Then you can bypass. Okay? But you have to wait 1 cycle. It depends on how long does it take, the operation latency. If it's a single cycle, you can bypass. More than 2 cycles, you have to wait 1 cycle or more. Okay? That is called bypass. Okay. That's the mechanism for true data dependence, and I'm explaining the materials you have studied in your undergraduate course. Okay? Another dependence, there are 2 other dependencies, write at write or write at read dependence. Write at write dependence means 2 instructions are writing to the same register file. If they are done sequentially, one by one, it will be okay. But in a pipeline processor, it can cause problem because depending on the instruction, the operation latency is quite different. Let's say the first instruction is an integer operation and writing to register R1. The second instruction is integer operation, but it's a multiply or divide. It takes, maybe assume that it takes 5 cycles. Okay? In a non-pipeline design, you complete first instruction and then you complete the second instruction. So they write this data in program order. It's okay. But in a pipeline processor, there is no read after write dependence. So they can move forward. Okay? You write into register R1 and complete. Okay? And then the second one, it takes longer. Okay. Assume the first one takes longer and the second one takes 1 cycle. The first one is 5 cycles. It takes 5 cycles, but the second one goes to execution stage and write back. But the first one is still working on. After the computation, it overwrites the data written by the next one. Then, when some new instruction is reading this R1, the problem is it should read the new value written by the newest one, but it's reading the old value written by the earlier one. Okay? It can cause problem. So, what should we do? Every time you check write after write dependence, if they are writing the same register, if it takes longer, okay, then you have to store the instruction behind because you have to wait. Otherwise, the write might be out of order and it will cause problem later. Okay, that's called output dependence. So output dependence can cause also problem. The other is called write after read dependence, and this is reverse order of read after write, so it's called anti-dependence. it can cause problem as well. Write after read dependence means you have to write after the previous one reads. This is normally preserved. So the violation can happen. There are two instructions. It's reading register R1. It's writing to register R1. This is an earlier instruction. So it should read first before this one writes. And that should be in general. But in out of order processors, it's possible. Even though this one hasn't complete, this might be waiting in some instruction buffer or instruction window. This might be issued out of order to the backend because there is no read after write dependent. Before this one reads R1, it's execute and it override R1. So it actually, when it reads R1, it's reading a value from the future. Okay, it's called write after read dependence, and that violation can happen in out of order pipeline. Okay, so we have to preserve this read data dependence. So before we go into out of order pipeline, let's look at the in order pipeline. So in order issue, if an instruction is stored in the pipeline, the following instruction cannot proceed. Usually, if we talk about fetch, decode, read, execute, write back, instructions are stored at the read stage. When you're trying to read source operand, you check read after write dependence, you store. For write after write dependence, you also store at the read stage because you usually put this dependence checking at the same stage. So for your read stage instruction, you check read after write dependence between the instruction at read stage and the producer in the earlier in the pipeline. Okay, if there is a write, and if this is trying to read, then you have a read after write, which means you have to wait the producer complete. Okay? Write after write is you also check. You have a write and there are some other writes. Okay? And some other writes are take longer. Then if you allow this instruction proceed, then this might write earlier and then it may be overwritten by the earlier instruction. So you have to stop the instruction at the read stage if there are write after write dependent. Okay? Once the instruction at the read stage is stored, decode stage and fetch stage instruction must be stored as well because it's blocked by read stage instruction. They cannot move forward, it's blocked. Okay? That's the in-order issue. To implement in-order pipeline, you need to check this dependence, whether if there is a read after write or write after write, which means you need register number comparators between the read stage instruction and execution and write back stage instruction. Okay? If there is a read after write or write after write, then the instruction at read stage must be stored. So let's look at some simple example. Let's say in this architecture, we are assuming single issue, 5-stage pipeline. So you have fetch, decode, read stage. So instructions are going through this pipeline. At the read stage is issued to the backend. Backend, you have 5 different units, 2 integer ALU. So integer ALU, you have 1 cycle execution and then write back. And there are 2. For floating point, it takes 4 cycles. For memory, it takes 2 cycles, and there are 2 memory pipelines. So instructions are going to this. This is called instruction pipeline. And these are called backend pipeline. This is integer, ALU. This is floating point pipeline. This is memory pipeline. Integer operation takes only one cycle, so there is no pipeline. You don't have to implement pipeline. So you compute and then you write to the register file. For floating point pipeline, it takes 4 cycles. Pipeline means every cycle it can accept new floating point instruction. Okay? You have 2 options. Either you can implement this way, floating point pipeline, or you can implement this way. This takes 4 cycles. So this is floating point unit without pipeline. This is different. So this means the operation takes 4 cycles and then it completes. So during this 4 cycle, it cannot accept new instruction because it's busy. This one is pipeline. You divide the execution into 4 different cycles. Every cycle, it can accept new floating point instruction from the front end, from the instruction pipeline. Okay? Memory is pipeline. Operation takes 2 cycles, but every cycle, it can accept new instruction. Okay? So assuming we have this kind of back end and front end, we need to check read after write. So if the consumer is here, producer is somewhere here, then it can be a read after write dependence. Right? So producer is in the pipeline. The consumer is trying to read the same register. And you need to check this read after write dependence. If there is a dependence, you have to generate store, which means you have to recycle the instruction until the producer goes out the pipeline. Okay? So in this case, what should be how many register number comparators do you need to enforce read after write or write after write or write after read? So maybe you have to think before I explain. You have to think. So for example, if the consumer is at the read stage, there are instructions here, then let's say it's trying to read 2 sources and it's reading 1 destination. Assuming it has 3 operand instruction, 1 is destination, 2 is source. Each instruction might have 2 source and 1 write, okay, destination. This means if you have the same register number here with same destination here, if this number matches this number, then you have a read after write dependence instruction in this pipeline and instruction at the read stage. Okay? The producer might be any of these pipeline. So you have to enumerate the comparators. How many comparators do you need to check for read after write dependence and write after write dependence? Can you do that? Minji, do you know what I mean? You have to draw, and how many comparators do you need? You have to come up with. Okay? Can you do that? Do you know? So for read after write, you need 1 comparator, 1 comparator, 1 comparator, 1 comparator, and so on. Right? So you can count how many. For this source, you need another comparator, and so on. You count how many. You also need to write after write. Okay? So do your exercise right now. Excuse me?
How many sources do you use?
Each instruction have two sources and one destination. So you can use that assumption, okay?
Then source and length of execution.
Excuse-
Source, how many source and execution, operation length.
Operation length is specified by here. So integer 1, floating point 4 cycle, memory 2.
Number of operation length multiplied by number of source.
Okay, anyway, maybe let's talk about that later. Okay, let me explain. So let's focus on the instruction at the read stage. You have one instruction which has two sources, one destination. Let's focus on the first source. For this source, we are trying to identify read after write dependence, which means if there is any destination that matches this register number. So you have to compare this one with the destination number here. Okay? You also need to compare with this one. Okay? So actually you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Or something like that. So for each source, for read after write dependence, for integer, you have two stage, execution and write, and there are two integer ALU. Okay? So, for this source, you have two sources. For each source, you have, for integer, you have two stage, and there are two integer. Okay, because you need 4 times 2, 8 for integer, plus this one you need 5 stage, and there is only one floating point. Okay, so this one. For this one you have 3 stage, you have 2 memory, pipeline for each source. So these are the number of comparators to check for read after write dependence. So how many? This is 4, 6, 5. So 15 times 2. So you need 30 comparators for read after write dependence. Okay? So if there is this read after write dependence, then the instruction at the read stage must be stored without bypass. With bypass, you can remove most of one, right? But you need to check the dependence. For bypass, you also need to check the dependence. If you have dependence, so we need the bypass from here to here, here to here, or something like that. So you can bypass all these, but for these, you have to generate storage, because you cannot bypass directly. It takes more than one cycle. Okay? Clear? This is for read after write dependence. How about for right after right dependence? Right after right dependence is you are comparing this one with this one. So all the destination you are have potentially right after right dependence, right? But you don't have to have complete touch for this one. Not this one. This one. Okay, let me use another color. This one is okay. Compared to this instruction at the read stage. Right after right violation means some instruction earlier, that issued earlier, might overwrite the data if you allow the instruction to go forward. That is the right after right violation. Okay? The example was, let's say you have integer operation, and this is maybe floating point operation. And they are writing the same register. If you allow this one to proceed, maybe this one will finish in 2 cycles, execution and write back. But the earlier one takes 4 cycles, execution 1, 2, 3, 4, and write back. So whenever you have this kind of dependence, it will write to register R1, and then the earlier one, later it will overwrite the data. Then when the next time you read the R1, it should read the value R1 written by new one, but actually it's written by the old one. That is the problem. So it actually causes problem for long latency operation only. If it takes 1 cycle, it's okay, because the instruction at the read stage will take at least 2 cycles to finish the pipeline. And all these instructions, even though there are right after right dependence, this one is okay because this instruction will take at least 2 cycles, right? Wherever it goes, and this, by the time this instruction will all complete, right? So they will cause right after right violation. So you only need to check these, because these can cause problem. Okay? So you actually need 5 completers. 1, 2, 3, 4, 5 for right after right violation. Those can only cause problems. 창현 알겠나? 민지, 오케이? 쉽잖아. 뭐 어려울 게 뭐 있나? 그치? So right after right can happen only for memory and floating point pipeline, which takes more than 1 cycle operation. These long latency operation can cause right after right violation, but other, it's okay. By the time it should have completed already. So it will not cause right after right violation. Okay? And question? Okay. And in this pipeline, in this kind of in-order pipeline, there will be no right after read violation. So you don't have to check right after read dependence at all. And you can prove that. Okay? Can you prove? Can you prove? Dujin, can you prove right after read violation should not happen in this pipeline? And why? Can you explain? Think about it. Why right after read violation does not happen? Minji, you have taken my computer architecture course before, right? In undergraduate class. You have studied this issue before, right? Do you know the answer? Can you remember? Excuse me? There is no what? Can you show explicitly why that cannot happen? Right after read violation cannot happen? Any volunteer who can explain why the read violation should not happen in this pipeline?
The write operation preceded by some execution operation.
Excuse me, write operation?
Write operation, but before that there is some execution operation.
Execution operation, okay. So in that case, like that is not sufficient. I'm not sure.
Operations usually occur during post-operand. So post-operand already processed in read stage.
Mm-hmm.
So when write stage occurred after the orange.
That's partial. So to prove write to read violation should not happen, you have to suggest two conditions, and you are proposing only one. So what you are saying is, for each instruction, the read always precedes write because they are going through the pipeline in program order, right? Fetch, decode, read, execution, write back. So read always precedes write. That's what you're saying. But that doesn't guarantee. That's for only one instruction. You're discussing dependence between two instructions. Okay? You're discussing write of later instruction versus read of first instruction, whether this order can be changed. So you have to have another condition that relates it to instruction. Okay? So think about it. So you are proposing only one out of two. If you can come up with another one, then I'll give you bonus point of 5 bonus points. Okay?
Different temporary memory. Like integer, they read from the memory and they expect their own register.
I'm not sure.
Anti-dependency, say, processor, execution execution instruction in program order. And in the processor, it execute program instruction in program order. So here will not be
I don't understand clearly what you're saying, so can you be more specific?
If there is interdependency, it executes later instruction before than early instruction. But in the processor, it executes instruction in program mode.
Mm-hmm.
So there will not be
Conceptually, I think you understand. Okay? You need to relate your argument with his argument. Let me clarify. Assume that you have two instructions, instruction 1 and instruction 2. For each instruction, always you have disordering. Read occur before write because they are going through the pipeline. And for the second instruction, also the read precedes write. Okay, this is what you are stating, right? What you are saying. And what he's saying is, in order pipeline, between these two instructions, they are go through the pipeline in program order, which means between this read 1 and read 2, write 1 and write 2, I'm not sure, because they can they can complete out of order. But between the read, if this is an early instruction, this is a new instruction, then R1 always precedes R2. Okay? So this is some time ordering, topological ordering. Okay? So instruction 1 is earlier instruction, instruction 2 is later instruction. Okay? R1 always precedes R2 and R2 precedes W2, which means between these two, the instruction read of the first instruction should precede the write of the second instruction. Write to read violation happens when this order is reversed. But as I said, because this is always true and this is always true, this is always true, so it cannot be reversed. So, write to read violation may not happen in in-order pipeline. Kuyan, understood? Simple. This one always occur before this one, okay? This one always occur before this one, okay? So this one occurs always before this one, okay? The assumption of this one is earlier instruction, this one is later instruction. So can this be violated? Because this is always true. There will be no violation. Okay, so you don't have to have write to read comparators for this in-order pipeline. You don't have to check. For example, Itanium processor is a 6-issue superscalar. So there are more than 1,000 comparators to check read after write dependence and write after write dependence in Itanium. Because it's wide issue, you need to check lots of comparators. Okay, it has wide back end, wide front end instruction pipeline. You need to check lots of read after write after write dependence to generate pipeline interlock. But there is no single comparator for write after read dependence because it should not happen, even in Itanium, which is a 6-issue wide issue superscalar. Okay? Because of the same reason. Same reason. Okay. Let me ask you another question. We assumed this single issue pipeline with this instruction pipeline, and this is back-end pipeline. Back-end pipeline is our execution unit. This is integer ALU floating point and cache. This is integer pipeline. Every instruction goes through the instruction pipeline in program order. They are sharing. Okay? At the each stage, they are distributing to the back end. So you usually have narrow front end and wide back end. Okay? Because you have different functional unit for different type of operation. Is there something strange in this pipeline? Can you find any strange thing? So if I say, if Minji, let's say she studied in my lab and she become a computer architect. And he designed a new ARM compatible processor. Okay, same instruction set, different microarchitecture. So he's trying to avoid all this ARM license fee for their design. She came up with a new design, and she suggests this kind of architecture. Okay, professor, I come up with this design. This is a single issue with 5 functional units, and I installed each computer. It should work. This is simple 5-stage pipeline. And I say the design needs something wrong. Okay? It's not wrong. It should work, but it's not efficient. Can you find something wrong from this design? And if you give me a correct answer, I'll give you bonus point of 5 points. If I were a designer, I wouldn't design like that. There is something wrong, something flaw in the design.
Front end can give one instruction per cycle,
Mm-hmm.
but back end consume
Mm-hmm.
can 2 instructions per cycle
Mm-hmm.
at integer and memory
Mm-hmm.
stage. So one one execution unit can idle.
That's right. So what is your name?
이태우.
이태우 학생. Who is your professor? Who is your advisor?
육동석.
From computer science. That's right, I'll give you 5 bonus points. Okay? So what he's saying is, it's a single issue design, but you are installing 2 integer ALU, 2 memory. Okay, maximum, there is only 1 instruction. You don't have to have 2. 1 integer ALU, 1 memory pipeline should be enough. Right? Because the maximum you can send is only 1 instruction. If this is 2 issue, then it makes sense. Dual issue. So this is for dual issue superscalar like Pentium. Then this makes sense because you are issuing 2 instructions, you may need 2 integer ALU, 2 memory. Floating point operation is rare, so maybe 1 floating point unit. But memory and integer operations are quite common, so you provide 2 so that you can consume most of the time 2 instructions every cycle. Okay? So this is reasonable, but only 1. There is something wrong. Okay? Good answer. I give you 5 bonus points. Okay, send me an email. So I'll give this bonus point to your midterm exam. Okay? Minji, understood? Okay? 구현, follow? Okay, so let's move to out-of-order pipeline. So you now understand in-order pipeline, at least. Okay, let's work on out-of-order pipeline. In-order pipeline, the issue is every time there is a store in the read stage, the instruction behind at decode stage and fetch stage instructions are stored as well. They are blocked. Okay, but sometimes this is waiting for read after write dependence, so they have to be stored. But the instruction behind is nothing to do with the dependence. Sometimes you can execute if there is no dependence problems. Okay? That was the motivation for out-of-order processors. Can you do that? Can this instruction bypass earlier instruction in the pipeline and accelerate this pipeline? So here, in this example, the add operation is waiting for F0 because division operation takes time, and that produces F0, and it's trying to consume F0 and add is stalling in the pipeline. But there is another instruction, sub-instruction, which is nothing to do with this dependence. Okay? In normal in-order pipeline, this instruction has to be stored at, if this is stored at the read stage, this instruction should be at the decode stage and waiting. But we are trying to move this instruction ahead of this earlier instruction because it's okay, you can complete. Okay? That is the out-of-order machine, okay, dynamic pipeline. So, after Pentium, which is a two-issue superscalar design, Intel worked on Pentium Pro, which is fourth generation x86 processor. Okay? The time they increase issue is from 2 issue to 3 issue. So every time it fetch and decode and execute 3 instructions, it increase pipeline stage from 5 stage to 10 stage. It's more deeply pipeline so that they can increase the clock speed. Okay? And also, they work on out-of-order design. So in Pentium, every time there is a read stage stored, all the following instruction must be stored as well. But from Pentium Pro, even if you store, other instruction can bypass. Okay? In general, with out-of-order pipeline, you increased the pipeline complexity, or in terms of area, about 10%. It's more complex. You need instruction window, you need reorder buffer, you need more complex pipeline control logic. 10% additional cost. But the performance for integer benchmark, about you can increase about 30% performance. So you pay 10% overhead, performance is 30% gain. Much better, okay? That was the motivation for Pentium Pro. And this out-of-order pipeline is also called dynamic pipeline. And there are 3 approaches. And Pentium Pro's design was not new. Actually came from early IBM machines in 1960s. Okay? So everything was, the recursion actually starts from Ada, who is a daughter of Byron. Poet Byron, you know, English poet. So she actually proposed recursion, procedure, and all the current programming constructs using mechanical machine called Babbage, Charles Babbage mechanical computers. Okay? So actually in so that time frame is about 19th century. Okay? Before 19th century, the people, the women at Europe, they don't study how to read. They are they couldn't read the textbook at the time because there is some man versus woman, this kind of discrepancy, how to say, okay, the issue, okay. But that Ada was one of the genius, I guess. So he studied this. It's paper machine proposed by Charles Babbage. It was not implemented. And for the paper machine, the Charles Babbage machine has all these programs stored memory. You can store the program. You have input and output. Everything is same as current electronic computer, except it's mechanical. And for that paper machine, he proposed how to do the programming. And sometimes Charles Babbage tried to make comments on her programming notes, and it was wrong. And Ada is saying that do not mark any comments if you don't know anything, okay? So she had some authority in her programming. She was the first programmer, and named after her, Ada was the programming language for United States Department of Defense. Okay, it's one of earlier object-oriented style programming language, and from that we have C++ and Java and so on, object-oriented programming. Okay, and if you look at this pioneer, this out-of-order machine The scoreboarding was proposed by CDC 6600, which is early mini computer, early machines. And Thomas Law algorithm was implemented in this IBM 360 in 1967. And if you look at dynamic pipeline in current commercial processors such as i7, Pentium Pro, or Pentium 4, they all use Thomas Law algorithm, which was already proposed in 1967. Okay, but the same theory, same applies. Okay. Okay, let me explain a little bit about scoreboarding and Thomas Law algorithm. So what is scoreboard? Scoreboard. Scoreboard is a single bit flag for each register. If you have 32-bit register, you have 32-bit scoreboard. Scoreboard tells you, each bit tells you, if there is a register R0 to R31, you have 32 bits. Each bit tells you if there is a pending write in the pipeline. Whenever there is an instruction in the pipeline, you mark this score bit as set 1. That means there is some instruction writing to that register in the pipeline. There is an outstanding write for that register. So what you can do with scoreboard is sometimes you don't have to check read after write dependence. You look up scoreboard. If there is a write for R1, that means you are trying to read R1. There is a read after write dependence by looking up the scoreboard. Okay? That was the purpose of the scoreboard. Sometimes you implement it's comparator, sometimes you implement read after write scoreboard. But this is only for read after write. So anyway, the scoreboard is 1 bit per register, indicates whether or not there is a pending write. And pipeline stored on write after write. Okay, let's look at this pipeline. We have same pipeline: fetch, decode, read, execute, write back. Okay, same pipeline. And decode stage can be also called issue stage. Okay, issue stage. Decode stage, you check for write after write and structure hazard. For all these out-of-order machines, they have a buffer called instruction window between front end and back end. Okay? Before they issue to the back end pipeline, there is a buffer. Because the problem is, in the earlier, in order pipeline, if somebody is stalling at the read stage, you cannot progress because it's occupied. Okay? To make it out of order, this instruction you have to move to another buffer. It's called instruction window. Instead of occupying the stage, if you are waiting, you should not wait in the read stage, you should wait in the instruction window. Okay? So the other can bypass, other can progress. Okay? So all these scoreboarding or Thomas Law algorithm, there is an instruction buffer called instruction windows. You are waiting until the source operands are available. Then you can issue to the backend. Okay? So you can wait in this instruction window. Some instruction, you are waiting, but maybe later instruction can bypass before earlier, can be issued earlier than old instruction with this instruction window. So what they do at decode stage is they check for write after write hazard. That means they look at the scoreboard. If there is any pending write, then scoreboard tells you the bit is 1. Okay? This instruction is potentially will write to destination register R1. But before you issue, before you send this instruction to instruction window, you look at the scoreboard. And if there is another write to register R1, then you store. Because if you allow, then there might be a write after write violation. So you only allow only one pending write per register. Only one outstanding write for register. Okay? So pipeline stored on output dependence by checking the scoreboard, you allow only one pending update. Okay? And the instruction window is between this decode stage and register read stage. So after decoding, you send to the instruction window. Okay? But to send to the instruction window is a buffer. So there should be an entry, empty entry. If the instruction window is full, then you cannot issue. Okay? You have to store. Okay? That's for structural hazard. Structural hazard. So the pipeline also stores if there is no empty entry in the instruction window. So you can check write after write hazard, and you check for structural hazard for instruction window. If there is no pending write, then you can send this instruction in the instruction window. Wait there until the sources are available. So they are sitting in the instruction window, and they are trying to read source operand. Okay? They check read after write hazard. Okay? And whenever both source operands are available, then the instructions are sent to function unit in out of order, because you issue to the instruction window in program order, but it can be dispatched to the backend in out of order from the instruction window, because the order depends on whether your operands are available. Okay? Okay, so previously, from the instruction pipeline, at the read stage, you issue to the backend. Here, because you have this instruction window, it's decomposed into two different steps. One is issue to the instruction window and dispatch to the backend. Okay? The instruction sent to function out of order. So you check write after write, you check read after write here. Write back stage, once you complete your execution, you're trying to write to register file, but you have to worry about write after read dependence as well, because in out of order pipeline, it can happen. Somebody is waiting, your earlier instruction waiting, my source are not available. One source is available, but the other source is not available, I'm waiting. Another instruction, come to the instruction window, it can be issued. Okay, later instruction can be issued out of order. But this instruction is trying to write to the register. It hasn't read. Okay, there can be write after read violation. If there is a write after read violation, if some earlier instruction hasn't read your destination, then you have to wait there. So you check write back state, there is another store. You should not override, otherwise it can cause problem. Because then might read the new future value instead of the recent value. So this is quite complex logic, but it works. Okay. So they store on write after write hazard, they store on write after read hazard, and they can satisfy read after write hazard. And it should work. And this was employed in CDC 6600. But this is not actually used in modern microprocessors because it's not efficient. In modern microprocessors, they use Thomas law algorithm. Thomas law algorithm, you can eliminate all these output dependence and anti-dependence by doing register renaming by hardware. Okay? So you don't have to store on output dependence or anti-dependence. Output dependence or anti-dependence means let's look at output dependence. This one is writing to R1 and this one is writing to R1. This one takes too long. So it may overwrite this one. That causes problem. The issue is you write to R1 for the new one. You don't have to write to R1. You write to R10 instead. Okay? Every time you write to a new register, destination register. Then you can avoid this one. Okay? You read from R10. Okay? That is the register renaming. Let's look at anti-dependence. It's trying to read R1, right? But it hasn't read R1 because of the other dependence. This one is writing to R1, the later instruction. It bypasses and overrides R1. Then it causes problem because it's reading a value from the future. The problem is why are you writing to R1? You should write to R10. Okay? Then this one can proceed. Okay? This is register renaming. As long as you provide more registers for each destination, you can eliminate all this anti and output dependence. And this is started to be employed in Thomas Law algorithm and all the other out-of-order pipeline. Okay? So actually the same mechanism is used by, this is IBM machines, used by PowerPC. And Intel or other out-of-order pipeline, they sort of use Thomas Law algorithm, but they are somewhat different variation. So they use explicit register renaming, okay, logic to do that instead of Thomas Law algorithm, and they implement the same logic. Okay, and we study this core of out-of-order pipeline maybe next time. Okay, so you are now ready for out-of-order pipeline. Okay, 자 오늘 여기까지 합시다.